Hello everyone and welcome to the iSystem webinar series. Today's episode is about winIDEA 9.21, start of a new decade. We will inform you why we did significant changes to winIDEA and also how it looks like now with AMP and SMP multi-core configurations using a Traveo II and TC399 target board, for example. And furthermore, we will introduce a new feature to you called sampling-based profiling, which enables you to trace even if a controller has not enabled or implemented the on-chip trace logic. My name is Sabrina Kistlinger. I'll be the moderator today. Today's speaker is Chris Schlink, who will lead you through the technical presentation.
Hello.
Hi, Chris. Chris has been supporting iSystem in the Americas since 2004. He started as support engineer and has worked all his way up to senior applications and support engineer. His knowledge spans all areas of embedded hardware and software development, as well as testing on and off target and hill environments. So that's it from my side. And over to you, Chris.
Thank you. And welcome everyone to today's webinar, winIDEA 9.21, Start of a New Decade. What will the next 10 years bring to embedded hardware and software architectures, industries like communications, aerospace, consumer electronics, healthcare, industrial and IoT, energy, and last but certainly not least, the automotive and transportation industries, with the electrification of cars, motorcycles, buses, trucking, rail, and even personal aircraft, all highly sophisticated systems incorporating electrical, electronic, software, and mechanical components. OEMs and Tier 1s are also integrating components from other industries like communications and consumer electronics into their vehicles to satisfy consumer demand and differentiate themselves in the market. This creates extraordinary challenges for designers and engineers to overcome. Today we'll learn how iSystem is preparing to meet these challenges over the next decade. First, some general goals we hope to accomplish during today's webinar. You'll learn the motivation behind the new configuration changes in winIDEA 9.21. You'll learn how to set up winIDEA for two different multiprocessor configurations. You'll learn the benefits and use cases of the new sample-based profiling. And finally, you'll learn about the new built-in plugins for some of the most popular device families, like Cortex M and Oryx. Let's take a look at today's agenda. First, motivation. We'll take a look at what is changing in embedded systems development, including a brief look at hardware and software trends and how winIDEA is preparing for the future of embedded systems development. Second, we'll take a look at configuring winIDEA from scratch for two specific use cases, one using a hybrid AMP SMP configuration on the Traveo II 8M, the other using pure SMP on all 6 cores of an Oryx TC399, running AUTOSAR multi-core application. Next, we'll take a look at the new sample-based profiling feature. We'll cover 3 common use cases where the sample-based profiling can help during software development. Last, I'll briefly touch on the new plugins available in the latest winIDEA 9.21. According to industry analysts, automotive applications currently represent the largest use of embedded systems and will continue to outpace other industries. Automotive Mega-Trends like advanced driver assistance, vehicle-to-vehicle and vehicle-to-infrastructure communication, over-the-air updates, and self-driving are pushing the limits of automotive software systems and the hardware they run on. The modern vehicle EE architecture is rapidly increasing in complexity, combining both hard real-time systems with high-performance system-on-chip devices and POSIX-based OSs with multiple high-speed networks. Engineers must implement solutions that are also safe and secure. Here is an example of a sophisticated software architecture for a complex system on chip. The hypervisor provides isolation between and services to virtual machines running guest OSs. In order to properly support these complex software architectures and prepare winIDEA for even greater complexity in the future, we've made some important improvements to winIDEA's debug session configuration. I'll demonstrate two common configurations in winIDEA 9.21. The first use case is a hybrid AMP SMP configuration on the Infineon Traveo II 8M. The software architecture implements two applications, one executing on the M0 core and another executing on the dual M7s, configured as SMP. The second use case is a purely SMP configuration using AUTOSAR Classic, executing on all 6 cores of an Infineon TC397XE. Let's take a look at the Infineon Traveo II configuration. It features a hybrid of the AMP and SMP architectures where some homogeneous cores are clustered together and run an SMP OS, like AUTOSAR in this case. The heterogeneous AMP cores run their own RTOS or custom scheduler. In winIDEA's new session configuration, we need to create 2 application spaces, one for the app core 0 and one for the app core 1 and 2. Then we need to create 2 memory spaces, one for the AMP using M0 Plus core and one for the SMP configuration using the dual M7 cores. The boot core is always connected to the first instance of winIDEA. In this case, the M0 Plus is the boot core. The application space and memory space configuration is always done in the main instance of winIDEA. Now let's take a look at the Infineon TC399 running AUTOSAR on all 6 cores in an SMP configuration. In winIDEA's new session configuration, we need to create a single application space for app all cores. Then we need to create a memory space for the SMP configuration and map app all cores to the memory space MS app all cores. Now we'll go to winIDEA 9.21 and demonstrate configuring these 2 use cases. I'll go ahead and start by creating a new workspace. This will be for our Traveo II example. So one of the nice new features is this automatic blue box selection guide. It detects the blue boxes that you have connected via USB or Ethernet. So I'll go ahead and select my IC 5700 that I have connected. And here we have the basic session configuration dialog. This is a new dialog that allows you to set up the bare minimum to get up and running and debugging a single application. So let's set up the device that we're going to be connected to, the Traveo II 8M device. Now we want to select the symbol file. This is the ELF file. Typically the ELF file. There are other formats that we support, but ELF is the current standard. So we want to select the ELF file for the boot core. So in this case, this is the M0 core. If you have a different file that you program for code different than the ELF file, so the ELF file has both symbols and code, And you can load both from just the ELF file, or you can, if you want to load a hex file or a binary file that you actually program to the target, you can also select that file here. So this would be the minimum configuration to get up and running. I could either program or just load the symbols. If this code was already programmed to the target, I could just do a load symbols only and start debugging just with this configuration here. But since we're running a hybrid AMP SMP configuration, we still need to set up another application space, and we also need to set up the SMP configuration before we can set up the two memory spaces that we need to set up, one for the M0 core and one for the SMP configuration. So if I click Take Me There Now, this button here, we can go and set up the rest of the configuration. winIDEA has created a default application space for me. I can use this to configure the boot core, in this case the M0 core. So I can just click Edit here. I'll go ahead and change this to App Core 0. We'll make sure that the symbol file is already brought in here that we used in the initial setup. You might need to set up directories to the source files depending on where your source files are located. If the paths in the ELF files are correct or not, the source files will automatically be brought up in winIDEA if you're going to be stepping through code. If they're different or the paths in the ELF files are not valid on your local PC, then you'll need to set up the paths here. We can also set up the OS. So for this M0 core, it's just running some custom scheduler. I'm not going to be doing any task or ISR analysis on that core. So this is enough for the application space for the boot core or the M0 core. So now we'll set up another application space for the cores 1 and 2. This is for the dual M7 cores that we're running in the SMP configuration. So now we need to add the ELF files for those cores if there's one file or two files. In this case we have two files. So here's the first file for the first core. And then we have the second file for the... Okay, so this looks good. Again, you can set up the directories if you need to point to source. If you need to set up an OS, you can do that as well. This is good. This is what we need to set up for the AMP and SMP configuration. Mapping just the M0 core to the first application space and both M7 cores to the second application space. Okay, so now let's go ahead and set up the different memory spaces in the SMP configuration that we need to configure the rest of the system. So first we'll set up the SMP configuration, and we need to bind together both M7 cores. Let's call this memory space app core 1 and 2. Alright, so we've created our SMP configuration. Now when we go to the memory spaces, winIDEA has created these default memory spaces for us. So the core M0, let's go ahead and edit that, and we'll change the name to memory space app core 0. Yes, and we want to connect that to the M0 core. That's correct. And we are mapping this to the application app core 0. So that looks good. These other two that winIDEA created by default, we'll actually want to remove those. And we'll create a new memory space. So we'll call it MS App Core 1 and 2. We'll connect it to SMP configuration, and then we'll map it to the application space that we created for this cores 1 and 2. Okay, perfect. So this is exactly what we want. We have our 2 memory spaces, we have our 2 application spaces, and we've mapped the 2 together. So we have our mapping of the core 0 memory space to the application core 0, and the cores 1 and 2 memory space to the application core 1 and 2. So next we need to add the remainder of the ELF files, or files that we want to program. They don't necessarily have to be ELF files, but in this case they are. We'll add those to the system. So first we'll do the M7 core, and now we'll add the M7 core. Okay, and we can arrange them in any order we want. So winIDEA will program these in the order that they're listed here. Okay, so that looks very good. So the last thing we need to do here is just select the probe. So we're just using a passive probe. Now we can click OK. And that's the configuration. Now we'll just perform a download. Okay, so we're here at the reset vector. We can just set it to run. So now we can just let it run for a while. Maybe add a variable to the watch window so we can see everything's running okay. We can stop the system. So now let's take a look at the Infineon Oryx TC399 in an SMP configuration. We'll create a new project for the TC399. We'll select our IC 5700 here. Now we select the device we're going to be connecting to, the TC397XE. Now we grab our ELF file as usual. So in this case we actually have a single ELF file for all 6 cores. Now we're going to make the additional configuration for the SMP and mapping the application space to the memory space. So we'll use the configuration that winIDEA created for us. Here we have a default application space. We'll go ahead and edit that, and we'll just call it app all cores. You can obviously name it whatever you want. We have our single ELF file here that programs all 6 cores. This is actually using an AUTOSAR, so that's what we should select here. And in this configuration we are using an iSystem XML, and we have our profiler instrumentation.xml file. Okay, that looks good. So that's the application space. Now we need to create the SMP configuration and the memory space and map the application to the memory space. So here we're going to select the SoC and edit that. We're going to go to SMP, add, and we're going to select all the cores that we have in our SMP configuration. So that's all 6 of the tri-core cores. We'll call it ms underscore app all cores. Now we need to go to the memory spaces. None of these are, so these are all the default configurations. We could leave these here if we want. That's fine, I guess. Or we can remove them. I'll go ahead and add the additional memory space that we need. We'll call it ms app all cores. Now we create it using the SMP configuration that we just set up, and then we map it to the application that we have. And that's all we need to do. That's the configuration for the 6-core SMP. We've got our single application, we've got our single memory space spanning all 6 cores. We don't need these other cores here. I'll just go ahead and remove them. Okay. In case we wanted the HSM, I guess we could have left that one back there. So we'll just add back HSM. And that's really the only 3 cores that are possible in this case. Okay, so that's good, and we have our program file. This is the file that we're actually programming. If we need to program additional files, S records, binary files, hex files, you can add them here. Now we just need to perform a download and get to debugging. Alright, so let's go ahead and perform a download here. Alright, so we're connected, sitting here at the start address. We're in CPU 0. We can see in SMP mode which core we're stopped in. So if we want to view the other cores, we have an SMP option here now. We can actually view the other core in this same instance, so just a single instance of winIDEA for all 6 cores. So let's go ahead and just run. Okay, so now I ran the whole system. Now CPU 4 is also running. You also have a process, so if we had different applications that we were debugging, we could select which process we want to debug. Let's take a brief look at the new analyzer configuration in winIDEA 9.21. Now the setup reflects the address and memory space mapping. We have a new process selection where we select which process we want to trace. I set up a trace for the SMP system using all 6 cores. We have a custom instrumentation to gather thread and runnable data from the OS for all 6 cores. We use an iSystem XML file with the TC397XE, which is an emulation device from Infineon that has a hardware trace interface. We're going to manually configure the hardware trace to record 2 variables over the Shared Resource Interconnect, or SRI. We have our system trace variable and our iSystem trace runnable variable. These variables provide runtime status of the 6 cores, threads, and runnables, which are the software components of the AUTOSAR OS. We're using a 2-second limit session duration option. And then in the profiler section here, we're just selecting OS objects. And we have thread name and runnable name. These are specified in the iSystem.xml file. So the CPU is still running. We can go ahead and just start the trace. And so now the trace is sampling. It should sample for 2 seconds and then stop. And then we'll be able to view the results of the trace. And so just as always, you have your runnable data here in the code section, and then you have all of your task and ISR data in the lower data section. And then you can view anywhere in the timeline and zoom in to see what exactly was happening. And of course, you can right-click on any one of the runnables or tasks to get further information, timing on the specific number of calls that were made, the time it was spent, any nested calls, any interrupts, and the period data. And you get that for all runnables and tasks and ISRs. Now let's take a look at the new sample-based profiling feature. Anyone who has ever used a trace interface knows the power and control it provides over software development and especially timing analysis. If you have the ability to set up one or more of your development systems with an emulation device or a special mock-up to get trace, we will always recommend doing so. But sometimes a trace interface is not possible. In those cases, the sample-based profiling can be very helpful. The way it works is the debugger can read out information like the program counter or variables and data from the target during runtime. The blue box provides the timestamp for each read, and the information can be displayed in the analyzer, profiler timeline, and statistics views. Depending on the use case, the profiler can process this information in 3 different ways. Function load, when sampling program counter, OS task ISR2 load, when sampling current running task and ISR variables, and DAC, when sampling variable data. What exactly does this information provide? What needs to be understood here is that we are sampling these values over time and not reading all the values, nor do we know when specific events happened. What we are providing is a snapshot of the program counter over time. This provides a statistical load analysis over time, not a real-time analysis of execution. This also depends on how frequent the system can sample the PC register. The higher the sample frequency, the greater the accuracy of the load analysis. Sample the current running task and ISR variables to get a view of what tasks and ISRs are doing over time. Sample any value and display it over time with other sampled data. View statistics on the sampled data in the Profiler Statistics window. Important things to know. This new feature is only supported on the IC5700 platform, both passive and active probes. No trace hardware is needed. You do, however, need a trace license for the specific architecture, like an ARM trace license or a tri-core trace license. The data sampling and OS load, task, and ISR sampling is supported on all architectures, but the PC sampling is only supported on Cortex M, A, R, and tri-core. It is not supported on PowerPC or RH850, as they don't support reading the PC during runtime as required. The actual sampling rate will depend primarily on the debug clock and the number of sampled objects. Let's take a look inside winIDEA how to configure the new sample-based profiling feature. I have the analyzer window open, and now we'll take a look at the 3 different configurations for the sample-based profiling. First, we'll look at the function load analysis, which samples the PC register over time. So first you want to select the process that you want to run the load analysis on, then go to the profiler section. Here we want to go to the data section. We can click new, and we have these new data sampling and PC sampling options. So we'll want to select the PC sampling, and all we really need to do is provide some kind of name here. And winIDEA automatically configures itself to record the PC register over time and display that information in the profiler window. So I already have a configuration set up here, and literally it's just a name. So since we're sampling the PC, you can filter out certain functions, but it'll still sample the PC as fast as it can, and it'll gather as much information as it can, and then whatever you choose to remove or not view will just be removed from the display. It won't. It has no idea what it's actually sampling. We're just sampling the PC, and so whatever data we receive, we then display, or we don't display it if you don't want to see that information. That's it for this PC sampling configuration. So now we can just run the trace. The CPU is already running. We can see it's waiting here. I actually have a trigger set up at an end condition, so we will never meet that end condition, but it's recording the PC right now. So I can just stop it at any time, or if that end condition were to hit, we'd see the trigger and the trace would stop. I'll just stop it manually. And winIDEA is now loading the information, and we can just kind of zoom out to see. So I recorded just shy of 20 seconds worth of time sampling the PC register. And so the type of information we're given, it just shows us where it's spending most of its time. So where is the PC happen to be, what value does it happen to be when we sample it? And then we give you statistics on when in time does it happen to be more of a certain task, statistics on the data that we've collected. So it basically is giving you different information than a typical hardware trace would give you. So again, this is done without any hardware trace. We're just using the JTAG or the DAP or the SWD or whatever debug interface we have, but it's not a trace interface. And we're just sampling the PC register. So not a replacement for a trace interface. If you have access to one, we definitely still recommend utilizing that trace interface, because then you'll get much more accurate and precise timing measurements. Now let's take a look at the OS running task load analysis. Here we're actually sampling the current running task variable that the OS uses to keep track of the current running task. So again, we select the process that we want to use. We go to the profiler here, and we've made it as easy as possible. So just like you had a hardware trace, you would just select the OS objects option and the different objects that you wanted to try to monitor, and winIDEA handles it. In this case, we're actually using a profiler XML file that describes the variables that we want and actually the access that we want as well. I've got the XML file up here, and so the kind of magic tag here is that we're going to use the DAC acquisition, and we set up the sample pool size here. And so we do that for each variable, and then we specify this XML file in winIDEA for the sample-based profiling to use. Okay, so we have that selected. Let's go ahead and run this. So we'll let this run for a little bit. Again, it's showing waiting. The end trigger event never hits here. So we can let this run for a bit. I'll go ahead and stop it now, and we'll take a look at the results. So in this case, we'll actually need to open up the data section of the profiler timeline to see what's going on. We have our data section here. We can just zoom all. So you can organize it to see which tasks were active, the most active over time. And so really there were only a few tasks active, but we can get some percentages to see which tasks were the most active. And again, this is just a rough estimate of what's going on. We're just sampling the current running task. We're not seeing when these variables are changing or even if we're getting every value. So this is just a load analysis. Now let's look at the final sample-based profiling use case, which is the DAC data. So this is basically pulling variables over time. So let's look at the configuration there. So again, we're going to select the process, go to the profiler. We have 3 variables that we've set up here. So we use the new data sampling option. So we can provide a description. We're going to specify the variable, obviously. You can set up a sampling interval, so fastest, normal, or slow. auto size, we can set the interpretation to a regular variable. Okay, so for these three variables, let's go ahead and take a look at what we have. So the CPU is still running. We'll just go ahead and run the trace. So again, it's showing waiting, but it's recording. If it were to hit my trigger event, then it would show stopped. I have it actually to stop the system on the event. So okay, so let's take a look at we have a nice plot of the values over time. We can look at any slice of time to see what the three values are. We have some basic statistics here on the values and what values they were over time. So that's it for the sample-based profiling features. The last item on the agenda today is the plugins. So we have a new architecture-based plugins which will differ depending on the device you've selected in winIDEA. So today I'll go over the Oryx and Cortex M plugins. So first let's take a look at the Oryx plugins. So the MCX plugin provides a separate core view of the multi-core cross-connect. Clocks provides the real-time view of the STM, MCDS, and SRI clock frequencies. The UCB plugin provides access to the user configuration block memory, which is essential for proper functionality. And finally, the reset control unit, which will tell you what the source of the last reset was, which can be very helpful when encountering unexpected resets. Then you have the counters for all of the 6 tri-core cores. Then we have our standard built-in iSystem plugins, the XCP plugin, breakpoints plugin, the Hill monitor, as well as the measurement and health plugins. And the last is the AUTOSAR Objects View plugin, which only will update when the CPU is stopped. If you're using any kind of operating system, AUTOSAR operating system, you can view stack usage, all kinds of information, but this information can only be updated when the system is stopped. And now, wrapping things up, we have the Cortex M plugins. First is the Cortex MPU. It's a SOC plugin that is used to view the number of Cortex M MPU regions with the location address, size, access permissions, and memory attributes of each region. The Cortex M MPU supports the following architectures: ARM v6, ARM v7, and ARM v8. Next we have the Cortex Fault Reports plugin for winIDEA. This is used to view Cortex exceptions and the exception context. And finally here we have the Cortex Status plugin, which displays various cycle counts, which are memory mapped in the device watch point trace unit DWT. Cycle count displays the count of cycles while the CPU is running and calculates the execution time based on known CPU clock. CPI count displays the amount of cycles beyond the first instruction cycle. Exception count displays the count of cycles spent in the exception processing. Sleep count displays the count of cycles spent sleeping. LSU count displays the amount of cycles spent processing load store operations. And fold count displays the total count of folded zero-cycle instructions. In summary, we found out that the future is driving important changes in winIDEA 9.21 and beyond. We learned how easy it is to use the new debug session configuration approach to debug complex hardware and software architectures. When you don't have access to a hardware trace interface, try the new sample-based profiler to analyze what the OS or function load is over time. And finally, don't forget about winIDEA's built-in plugins, as well as the popular device plugins. Thank you all for your time.
Thanks, Chris, for sharing your knowledge with us. It was very interesting and a good overview, I think. And now, please don't forget to download the presentation by clicking the cloud symbol top right of your screen. And let's come to the Q&A session. Chris, I have a very important question, at least for me. You mentioned this health plugin. What is it? Does it count my calories or my steps? I never heard about this. So what is it?
Yeah, so it's not quite that type of a health plugin, but it provides some information about the health of the blue box that you have connected. So some like temperature information and voltage information.
Okay, so I cannot use the IC5700 for sports and some
No,
activity
yeah,
analysis.
there's no iWatch connection for monitoring.
Okay, thanks, Chris, and back to serious now.
Yeah.
There are a lot of customers out there using older versions as 9.12 or 9.17. Is it a smooth upgrading to 9.21, or is there anything the users should know about it?
Yeah, so there is a smooth process. Basically, winIDEA opens up the workspace and it backs it up, and it does a conversion to the new winIDEA 9.21 format. So it should create the application and memory spaces properly. You should double check the trace configurations. If you have any existing trace configurations, those might need to be updated manually.
Okay, and if someone creates a workspace from scratch in 9.21, is it also backwards compatible?
I don't believe it is, to be honest. I'll have to double check on that, but I don't believe so.
Yeah, I also don't believe, honestly. Yeah.
Yep.
Yeah. Coming to the SMP configuration, you showed if you have mapped all the cores and one of the cores hit a breakpoint, what happens to the other cores?
So this actually depends on the architecture that you're using. So most modern processors do allow some kind of synchronization to stop all the cores when one of the CPUs stops. So the synchronization of the start and stop of the cores, maybe in an SMP cluster, is mainly realized within the chip. So the winIDEA debugger really only configures the chip to the certain configuration that you want to set up. So on targets like Oryx or Cortex, such core synchronization is supported and used by winIDEA. So we have AMP configurations. They may or may not be synchronized. It's basically totally up to the user.
Okay. I have another question. When I think back when you selected the MCU in the MCU selection pop-up window, I have the impression that you can now type in the derivative or parts at least, and you don't have to go all the way through architecture, family, and then scroll down as it was before. Was that my right impression?
Right. Yeah, exactly. So we've basically made one master list of all the architectures now, and so you can just start typing the name or even kind of a nickname of the architecture, and winIDEA should display the proper results.
Yeah, cool. I think this is really an improvement, just being able to type a nickname or parts of the controller name and not having to scroll through all the thousands of supported controllers we have in the meantime.
Right. Yeah. There's so many devices that it does help.
Yeah. Cool. And also coming to another tab, it's called memory space. It maps cores to a memory space basically. So this is a function. So why is it called memory space? I think I'm a little bit confused here.
Yeah, so we tried to kind of give it a generic name. I do agree memory space may be a bit misleading. Perhaps a better name might be something like an execution environment or maybe execution context. So on a microcontroller, meaning CPU without a memory management unit, this is pretty much a core. So on SOCs with MMU and also an OS and maybe a hypervisor using the MMU for creating virtual memory spaces. This really means virtual memory space. So in that case, you basically need to specify the context ID, and on a case on a hypervisor using hardware virtualization, the virtual machine ID is what's needed. So such type of SoC and software architecture are purposely not covered by this webinar. So this would be a topic of its own for a dedicated webinar. Yeah.
All right, thanks for that, Chris. And I'm thinking just about the sampling-based profiling approach you showed. I think this is a very interesting approach to enable tracing without the on-chip trace logic. But maybe how about adding its instrumentation and using the debug channel to the terminal output? Wouldn't be that an alternative and better?
Yeah.
No?
Yeah, exactly. So something that's sort of forgotten about, like back in the old days of writing code and debugging on embedded systems, a typical technique would be like a printf type debugging, where you use small instrumentations in kind of strategic places throughout your code, and then when obviously when the code executes that location, you can get a nice little message on a terminal or something. So we still support that type of functionality in our tool. There's a small bit of code you can link in and then instrument your parts of your code that you want to see happen. That would, so depending on, so the way that the profiler, the sample-based profiling works is it's basically stealing bus cycles to read memory or read registers while the system's running. And so depending on how loaded your buses might already be, the instrumentation using the debug channel to the terminal output could be a more efficient solution. It wouldn't be loading the bus as much, not nearly as much, and you'd get much more specific information, just the information that you wanted. But for a very quick solution, and maybe you don't want to instrument the code because that's quite a process, the sample-based profiler is very useful in that situation.
Yeah, and it only works with the IC5700 and with winIDEA 9.21, right?
That's correct.
All right, wonderful. Thanks, Chris. I have no questions left, and obviously no other attendees have questions. So we are coming to an end to this session. So thank you very much. All questions we were not able to answer now will be answered by email afterward. And if you have questions also later, feel free to send us a mail to webinar@isystem.com or also reach out to your sales or tech representative at your iSystem global distributor. So thanks again, Chris. Thanks for sharing your knowledge. It was a pleasure. And bye, everyone, and take care.
Thank you. Bye.